Okay, so we're on page 10 in our notes packet, and we're going to look at 4.3, connecting f prime and f double prime with the graph. So we looked at a graph similar to this previously where we have local extrema, and we can have local extrema at some critical points, but sometimes it also fails to have local extrema at others. For example, here we have f prime is equal to 0. We can see there's a horizontal tangent, so there's a local maximum. However, here we also have a horizontal tangent because f prime is equal to 0, but there's no extreme value. So there's no extreme value because if we look at the graph, it's positive slope, and then it continues to have a positive slope. So the first derivative is positive, and then it stays positive. Whereas over here, at our other point where we said there was a local maximum, we see it's a positive slope and then negative slope, so it decreases. So it switches from the derivative being positive to negative. So anytime it actually switches signs, okay, so the sign of f prime, where that switches, that's where we want to look at maximum and minimums. If there's no change in sign, then there's going to be no extreme value. Here's another example. Here's f prime is equal to 0. If the derivative is negative, so it's decreasing, and then it continues to decrease. So there's no maximum or minimum at that point. So the first derivative test, this is where we create the number line that I introduced previously. So we're going to take a look at negative x squared. And we're going to use the first derivative. So that's going to be negative 2x. So when we set this equal to 0, when we set this, see where it's undefined, we see that we have a critical point at x equals 0. So we're going to create this number line for f prime. And here's 0. So we're going to plug in, let's say, a test value negative 1. Now remember, we're going to be plugging into f prime of x. So negative 2 times negative 1 is positive. And then let's say we choose a test value to the right of 0, say 1. So we'll have a negative 2 times a positive 1, which is negative. So our graph goes up, and then it comes back down. So we know there's a maximum. So we have a maximum f of 0, and if we plug in 0, we get 0. So anytime f prime changes sign from positive to negative at C, then we have a local maximum at that point. So the next one we want to look at is when it changes sign from negative to positive. Again, I use some basic graphs because I know that we're all familiar with parabolas. So when we go through the process here, we get 2x. Again, we set it equal to 0 to find out our critical point is going to be x equals 0. So I create my number line for f prime. So again, I'm going to choose values to the left, negative 1, so that'll be negative. Choose maybe a test value positive 1, so we get positive, so it goes down, comes back up, so we know that is a minimum. So we have a minimum, f of 0 equals 0. So again, just to remind you, it's going to change changes sign from negative to positive at C, then you have a local minimum. So next we want to look at what happens when f prime does not change sign. So an example of this would be x to the third, which if you can kind of picture what x to the third looks like, you know that. Right, so we know that there's no maximum or minimum, but we can show that through the first derivative test. So again, we're going to set this equal to 0. So we do get a critical point. Our critical point is 0 again. So we're going to do the number line for f prime. We put 0 here. So now if I choose a test value, say negative 1, remember we're plugging into the derivative, not the original function. We only plug back into the original function when we want to find the actual maximum or minimum values. So when we plug negative 1 in, obviously when that gets squared, we're going to get positive. And then of course when we plug in a positive 1, it also is positive. So it's increasing, and it continues to increase after our critical point. So since f prime is greater than 0 here, and f prime is greater than 0 here, it didn't it didn't change sign. So therefore, no extrema. So we can see no local extreme at C. So there is also the case where there's actually maximum or minimum values at endpoints. So at a left endpoint, if we have the derivative is less than 0, so in other words, it's decreasing, so it has a negative slope, then we know there's going to be a local maximum right here at this left endpoint. Right? So it's kind of starting up here and then it's decreasing. And then we also look at what if it's increasing, right? So here we look at the graph is going up. That makes this a local minimum. At a right endpoint, so if the derivative is less than 0, so if you look at leading up to that point, it's decreasing, and then right here it stops, so that's going to be a local minimum. And then here, if f prime is positive, so we have a positive slope leading up to that endpoint, that makes this a local maximum. Let's take a look at the first derivative test to determine local extreme values of the function and identify any absolute extrema, and then we'll support our answers graphically. So first we'll start out with finding the derivative. So that's going to be 3x squared minus 12. So we want to set that equal to 0. And we get, when we factor out a 3, we would get x squared minus 4. So that would be x plus 2, x minus 2. So our critical points are -2 and +2. Also, we want to just make sure that we consider our domain up here. So when we create that number line, we want to take that into consideration. So if we have a place where the graph is undefined, or it's not, for example, if it's a square root or if it's a rational function, we want to make sure that we don't accidentally include those in our intervals of increase and decrease. We don't need to worry about this because it's a polynomial, so it's going to be continuous everywhere. We're going to place -2, +2 on the number line. So if we test a value to the left of -2, again, we're plugging into the derivative. So here we get a positive number. Plug in 0, we get negative. Plug in something to the right of 2, we get positive. So it's going up, comes back down, goes back up. So there's going to be a max up here, a min down here. Again, we don't have to worry about any endpoints because this goes out to -infinity and +infinity. So this case where we had different cases for left endpoints and right endpoints doesn't apply to this particular problem because the domain is all reals, but we may see a situation where we do have to consider that. So we know that there's a max, and the max is going to be at -2, so it's going to be f of -2, plug in -2. Now we're plugging back to the original equation, so that should give us 11. And then we have a minimum, and that's going to be f of 2, and plug that back into the original equation. Now we get -21. Now, to support our answers graphically, there's a couple ways we could do this, but I think I'll just, we're going to just graph our original function. So we have x to the third, and then minus 12x, and then minus 5. Now, just looking at the numbers that we got for our maximum is 11 and minimum is -21. I think what I'm going to do is change my window a little bit. So, and again, since I'm looking at from -2 and 2 are where they're located, I'm just going to make my x min 4, x max positive 4. And then let's see, my x minimum, let's say maybe negative 25, and then we'll go to a maximum of, let's say, 15. So we'll go ahead and graph that. And it looks like, just by our window, it looks like we do have the correct max and min. So let's double check. We'll go to second trace. We'll do maximum first. So I'll go over to the left and then to the right. And we get negative 211. Good. And then we'll double check with the minimum value. So we'll go to number 3. And we'll zero in on this point. And then we'll go to the right. And we do get, of course, we know that our calculator sometimes has trouble rounding, so we can assume that that 1.99999 so on, that's going to be 2, negative 21. Okay. Let's take a look at the next example. So in this case, again, if we just want to consider the domain real quickly, the domain is going to be, well, this will be all reals and all reals. So negative infinity to infinity. So again, we don't need to worry about any endpoints in this situation. So let's take a look at the derivative. We're going to use, looks like the product rule. So we have x squared minus 3 times the derivative of e to the x, which is e to the x, plus the derivative of the first part, which is 2x, and keep e to the x the same. Now, in this situation, I would factor out the e to the x. So when I factor out e to the x, I get x squared minus 3 plus 2x. By rearranging these, I notice that this actually factors. So when I factor, I get x plus 3, x minus 1. So by setting this equal to 0, e to the x, we know that's never going to be 0, so that's not going to give us a critical point. However, negative 3 and positive 1 will give us critical values. Again, e to the x will never be equal to 0, so we don't need to worry about that one. So let's create our number line for f prime. We're going to place negative 3 and 1. So when I test a value to the left of negative 3, so let's say negative 4. So if we'll go back to looking at this one in particular. So obviously this is always going to be positive, so then I check basically these two. So negative 4 plus 3, so negative times a negative will be positive. Next one, I pick something between negative 3 and 1, say 0, so it'll be a positive times negative, so negative, and then to the right of 1 will be all positives, so it's going to go up, come back down, go back up. So I have a maximum and a minimum. So my maximum, f of negative 3. So remember, we're plugging it back into the original problem. So that's going to be negative 3 squared, which is 9. Minus 3 is 6. So 6 times e to the negative 3, so 6 over e to the third. And then our minimum is going to be f of 1, and that's just going to be negative 2e. Next, we'll take a look at concavity. Okay, so next again, we're going to continue with concavity. And how do we determine concavity? Well, this is where the slope increases or decreases. So if we take a look at this graph, if you look at the slope and you see there's a number of lines drawn here. So as we go further up on the curve, the slope is getting smaller and smaller and smaller. And eventually, if you look at right in the middle here, it's 0. And then when we look at over on the right side of the curve, if you look at the slope, it starts out small and it gets increasing, and until it looks almost like a horizontal. And this is just specifically for y equals x to the third. So how do we know if y prime decreases or y prime increases? So that is basically going to look at the slope of the slope. If we look at the next page, the concavity test, if we know, so it's going to be concave up on any interval where the second derivative is greater than 0. So that means y prime is increasing. It's increasing where the second derivative is greater than 0. And concave down where y double prime is less than 0. So again, this is the concavity test, and we need to make sure that the function is twice differentiable. So here's our example 2. We're going to use that concavity test to determine the intervals on which the graph is concave up and concave down. So I'm going to start first. We have our first derivative, so negative 4x to the third plus 12x squared minus 4. And then we're just going to continue. Since we're just looking at concavity, I just go straight through to the second derivative. So this is going to give us negative 12x squared plus 24x. Now, we are going to set this equal to 0. So we want to look where it's positive and negative. So it helps us to look at, on the graph, we're going to create a number line, but this time with the second derivative. So I'm going to take out a negative 12x, and I'm left with an x minus 2. So I look at that. It's kind of like critical points, but with the second derivative, we don't call them critical points. Critical points are specifically for the first derivative. So we just find the zeros of the function of the second derivative. Again, this is for specifically the second derivative. So when I create my number line, I'm going to label it as y double prime. Again, this is a polynomial function, so we would want to also just consider if it's rational. We want to make sure that it's, we're not including any areas where the denominator would be undefined. We don't need to worry about that in this case. We also don't have any endpoints because, again, our domain is negative infinity to infinity. So now I'm going to test values, but remember, we're testing them in the second derivative. So if I plug in, let's say, negative 1, okay, so if I plug in negative 1, I'm going to get a negative answer. If I plug in, let's say, 1, I'm going to get a positive when I plug into the second derivative. And when I plug in something, say 3, I'm going to get a negative again. Now I'm not going to put arrows up and down. Since this is concavity, we're basically going to, anytime it's a minus, I put a little curve that's concave down, and then concave up looks like that, and then concave down looks like that. Now in concavity, when we write out the intervals, so concave down, we always use parentheses here. Okay, so I know with increasing and decreasing, we could use brackets, but here we're just going to use the parentheses. So I have negative infinity to 0, parentheses union, and then 2 to infinity, and then it's concave up from 0 to 2. So again, always use parentheses with concavity. Okay, next one. So let's go through the process again. First, we're going to start with the first derivative. And notice here they gave us a specific interval from 0 to 2 pi, not including the endpoints. When we do the first derivative, we're going to get just cosine x because the 3 goes away. And then the second derivative, okay, so again, we're looking at where it's 0, so we're thinking sine inverse, we don't need to worry about the negative sign, we can just divide out by -1. So sine inverse of 0 is going to be giving us x, whereas sine 0, between 0 and pi, 2 pi, excuse me, is x equals pi. So again, keep in mind, kind of like here, these are like parentheses, our endpoints, that's what we're looking at for the second derivative, and we want to look at pi. So if we plug in, let's say, pi over 2, plug that in, we get negative. Again, we're plugging into the second derivative. And then if we plug in, let's say, 3 pi over 2, we'll get positive, so it's going to be concave down, then concave up. So concave down from 0 to pi, and then concave up from pi to 2 pi. So when we have a change in concavity, this is called a point of inflection. So again, this is where the concavity changes. So if it changes from positive to negative, that is the second derivative, or negative to positive, we have a point of inflection. So let's take a look at example 3. So example 3, we have y equals e to the negative x squared. And so we have y prime. Remember, the derivative is going to be e to the negative x squared times the derivative of the exponent. So that is negative 2x. That's our chain rule. That's our first derivative.